All right, so this is our recap video for our function notation. So first, from our intro notes page, a function is just a well-behaved relation. Every input, there's only one output. So a relation was just a connection between inputs and outputs. A function is where every input only has one output. So you can kind of see by this diagram that I have here that every function is a relation, but not all relations are functions. We like to use function notation when we talk about our functions. That way it helps us know inputs and outputs without having to list extra information. So this symbol here is pronounced f of x, and that's short for function of x. So when we look at it with a rule like this x in the problem doesn't actually exist within the equation. We can't multiply, divide, combine. We can't do anything with this one. It's only there for a little bit of a placeholder, and you'll see kind of how it works on the next few examples. So x is our input. Everything over here on this side is the rule to determine our output. And then the f of x, this whole thing, represents the output. How function notation works is you have your function with your rule, and we're going to plug in any input value that we want. So with this table, actually I need to bring that back down, I guess. I'm going to plug in a number, any number I want. Let's say 3. How our function notation uses this 3 is like this. I have now plugged in 3 in the x column, so everywhere I see x, I'm going to replace it with that input. Like so. F of 3 equals 6 plus 3. And so in the end, we get a statement that says this. Where our normal spot of our table would say y, with function notation, it now says f of x. It's really just a fancy way of writing y. So I plug in 3, my output is 9. The power in function notation is right here. Without having to write extra stuff, I have what I plugged in, and I got what I got out in our equation. So if you just saw y equals 9 in a kind of our old notation, you'd be wondering what was the input, x equals what? But if you saw f of 3 equals 9, you automatically know, oh, x is 3, y is 9. You have both pieces of information without having to do any extra work or write anything extra. It's all in this one concise location. Functions can be any rule that we want. So this is our square root. So again, y is now used as our f of x. And let's plug in a number like 4. So f of 4 equals the square root of 4. So I need one number that when multiplied by itself gives me 4. There's actually 2 answers. It's 2 or negative 2. More commonly written, plus or minus 2. So over here, plus or minus 2. Maybe we plug in 36. So f of 36 equals the square root of 36. So f of 36 is equal to plus or minus 6. And that's how we use our notation. If there's a rule with multiple x values in it, we are going to plug in x every time we see x. So let's plug in a 2 for this one. So we get f of 2 It becomes 2 squared plus 2 times 2 plus 1. Every time you plug a number in, you have to give it parentheses. You have to put it in parentheses. You can't get away with not putting it there. You don't put the parentheses, the entire problem changes. For instance, right here, if I didn't put parentheses, I'd have 2 next to 2, and now it looks like 22. You might think, oh, let's put a dot instead. But the big thing, what if this was a negative? If I have negative 2 squared, that is 100% different than negative 2 squared. These are not the same answer. That's why parentheses are very, very important. So we get 4 plus 4 plus 1. So f of 2 equals 9. Functions are probably the most underrated thing in mathematics. We're going to take a look at how many different ways we can represent a function this next week. But right now, off the top of my head, I'm not 100% sure where this graph or where this function is when I graph it. I know it's a parabola because I've studied quadratics, so because of this 2, it's going to be a U shape. And I'm only quite sure where it goes. I think it's going to go like right there-ish. I'm not 100% sure. But if I were to continually plug in points, 2 is 9, I plug in 0, we get f of 0 equals 0 squared plus 2 times 0 plus 1, 0 plus 0 plus 1. Gives us 1. I could continually plug in more points. I could plug in 4. I could plug in negative 2. I can plug in 1/2. I can plug in all of these numbers, see what it spits out over here, and then begin to plot those dots. 2, 9. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm a little bit off on my drawing on one of my whatever. So it cuts up like this. 0, 1 should be like right there. So we can kind of see how it bends. But if we don't know how to graph it, we can plug in values and graph the dots as we go. Now we're going to use the notation. I'm going to move myself right here in the middle. Oh, I can't do that. I'm going to block the pen, so I'm going to put it right here. So f of x and g of x mean the exact same thing, but the only difference is name. So down here, if I said f of 4, you'd know that I want to use the f of x function with the input of 4. 5 times 4 minus 1. F of 4 would then be 20 minus 1, which gives us 19. If I wrote g of x, or give us an actual number here, let's say g of negative 2, I'd want to use the g of x function, not the f of x function. The different letter is really just a naming convention. So g of negative 2 gives us positive 4 minus 8 minus 1. G of negative 2 then becomes, what's that, negative 4, negative 5. Then the last thing we're going to look at is what's called a composite function, where we have one function that's using the other one within itself. So f of g of 3. So what this is asking us to do is first take the g of x function, evaluate it for 3. All right, so x squared plus 4x minus 1. So I have 3 squared plus 4 times 3 minus 1. So I get 9 plus 12 minus 1. So that's 21, so 20. So if I plug in g of 3, it spits out 20. I'm then going to use this 20, out of room again, and that's going to be what I plug in for f. So the answer to g of 3 was 20. So this was replaced by the 20. So now I have 5 times 20 minus 1. Oops. Gives me 100 minus 1. So my final answer to f of g of 3 is 99.